Okay, well, hello everyone. My name is Justin Essery. I'm an associate professor at Wake Forest University in the politics department, Department of Politics and International Affairs. Welcome to the International Methods Collouqium. The IMC is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by the National Science Foundation and Rice University. The IMC is affiliated with the Society for Political Methodology, who hopes that you will support quantitative research in political science by joining. The membership fee is just $10 a year for graduate students, and I will post a link to join the society in the Zoom webinar chat window after this introduction. This week's speaker is Ludovic Rheault, giving a talk entitled Modeling Audio Data with Speaker Heterogeneity. Ludovic's talk will last about 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window, and you can ask that question at any time, but we will hold all questions except perhaps for very, very short clarifying questions until the end of the presentation. A link to Ludovic's slideshow will be available in the Zoom webinar chat window so that you can refer to it throughout the presentation, and I will post that link right after we get started. Now I'd like to welcome Ludovic to the IMC. Welcome.
Thank you for having me, Justin. Speaking of the Society for Political Methodology, I should perhaps mention that we have a conference this summer, the annual meeting, which will be virtual. So thanks to Justin, we have a good idea of how it may look like. So I hope some of your viewers will consider submitting a proposal. I know it's a different experience, but given the situation with COVID-19, it was the only possible way to move forward. So, so thank you for having me as a guest in this colloquium. Today I'm going to talk about a project involving the analysis of video files. This project involves a co-author, Sophie Borwine, who should be in the audience right now. Sophie is a PhD candidate in the Department of Political Science at the University of Toronto, and I'm an assistant professor at U of T. So in this project, our goal is to implement predictive models. We want to predict attributes of speakers in political videos. You might be wondering why prediction, why using machine learning to trying to predict things. Well, consider this. In the US alone, the C-SPAN collection is over 250,000 hours of recordings. So if you were to ask a research assistant, an undergraduate student perhaps, to perform manual content analysis of this video collection, it would take 30 years, over 30 years without sleep, 24 hours a day, in order to just watch these videos. So we need powerful and accurate models to quantify attributes of interest from these videos. So we're interested in in comparing different modalities. So from these political videos, we could extract the transcript, the textual transcript, which was usually the option by default that people were using in the past. But we can also extract the WAV file, the audio, and we can also use the images, the visual modality from these videos in this talk. So just because it's too long to cover the three, it would be too long to cover the three modalities experience has shown, I will focus on text versus audio. So comparing the predictive accuracy of machine learning models that are designed to predict attributes such as the sentiment, positive or negative, the level of activation, whether a speaker is aroused or calm, and a specific emotion that is of interest, theoretically anxiety. I will discuss the methods that we'll be using are from the family of deep neural networks. And I will try to make this interesting for you in the audience who may be interested in using text as data or audio as data in your own research. I'll introduce concepts in transfer learning. So the models that we're using today all belong to a family of models that we could that rely on transfer learning. So I'll emphasize that concept and also mention some issues that we have to deal with when studying audio data. So I just want to emphasize that this topic seems to be booming right now. If we look at the past few years and you look at the main conferences in political science, we see a ton of research using audio and video data. I won't have the time to mention them all, but Bryce Dietrich and co-authors have published a very interesting work using the pitch of the voice of a speaker's voice or of a politician's voice as a measure of activation. There's Nux and Lucas. In fact, Christopher Lucas did an IMC talk some time ago, a great talk, and they are using an approach, they're proposing a hidden Markov model. So my talk today will be different. I'll focus on there's like two main families of models to study the audio data, hidden Markov models and deep neural networks. So I'll focus on the other families, so that will bring some variation or novelty. I'll try to avoid redundancies, of course, relative to this previous talk. Also, Marcus Newman did some fantastic work building upon phonetics theory using audio data and so many others. So it's a topic that is booming, and therefore I'll try to share interesting insights and experiences using audio data during this talk. You may be wondering why sentiment or activation in particular. Well, sentiment analysis, when I teach methods for text as data to graduate students, one of the most frequent interest of students is sentiment analysis. You can do a lot by measuring sentiment, which means whether a speaker or whether a text is positive or negative. For instance, it can help us to quantify political behavior and attitudes. We can learn if we're able to have a reliable measures of sentiment, we can learn how politicians feel about issues, what is their stance, whether there's a polarization between speakers, whether they are hostile to each other. So there's a lot of possible applications when being able to measure emotional states, and in particular anxiety. There's a long history of work in political science, which I'm pretty sure you've heard about. In political behavior, for instance, this famous book by Marcus Newman and McEwen, Affective Intelligence and Political Judgment, I believe was the title, and fantastic work that pinpoints or identifies anxiety as a fundamental emotion that affects behavior. And I think this couldn't be more spot on theoretically. If you think about it, we're all feeling anxiety all the time, every day. You may be anxious about graduating, about the job market. You may be anxious about an upcoming conference, about making a public presentation. All this emotional state, anxiety, in turns affects how we behave. It affects the decision-making process. There's a huge literature on that. So that's why we're particularly interested in anxiety as a specific emotion. But more generally, the two, aside from anxiety, which is a categorical or specific emotion, we can represent two dimensions of interest. So in this figure here, that's the circumplex model of effect, where you have one dimension on the axis ranges from negative to positive, that's sentiment or valence. And then on the north-south axis, you have arousal or activation, whether a speaker or someone is agitated or calm. So this is the, in a nutshell, that's very brief, that's the theory behind the choice of labels, of annotations for videos. So our data, so I want to raise a number of issues here. We have a video collection that is in progress. What we do, we take large collections of videos, recordings from Parliament, from the US Congress in particular, and the Canadian House of Commons, and we cut clips, and then we have them annotated. At first we have a subset of the data annotated by graduate students, but right now we're using MTurk workers. We have the three binary annotations. These are the three measures that I just mentioned: sentiment, activation, anxiety. And right now, this collection isn't finished, and it will become clear, I think, why it's complicated. That's probably the most difficult part of the process, is to obtain high quality data. And right now, what we notice is that whenever you ask human coders to annotate a video and tell us, for instance, is the speaker positive or negative, or agitated or calm, it's very difficult to have a good intercoder reliability. So I will present today results and compare our videos that are coded unanimously by human coders, and therefore for which we have a high reliability annotation, those that have a lower reliability. But right now we're in the process of replicating our collection and adding videos to ensure that we have high quality annotations. By the way, we will release this data set publicly, so we really welcome feedback, because we're in the process of doing it. And just to illustrate how complicated it can be, so we have thousands of hours of videos, very long videos. We use deep learning and machine learning through this process itself to prepare the videos. So we randomly select clips between silences. We filter them because we want to recognize whether there are two speakers interacting with each other. We want to know who that speaker is. So ideally, we want only one speaker per video. So we're using face recognition to ensure that the face in the foreground is the same and there's only one person speaking through the entire duration of the video. We pass that to our mechanical Turk coders. And finally, we get our video clips, which are usually between 5 and 25 seconds. They represent roughly one sentence. And we have annotations for sentiment, activation, and anxiety, as mentioned before. So upcoming steps, we're still improving this data collection right now, and we'll also so some of you may wonder, well, why not finding a better way than having human coders watching the videos and telling us whether a speaker is activated or not? You might, there are maybe better ways. So one of the other things we do in this project is that, well, in fact, we're supposed to do that right now, but because of COVID-19, it's really not a good time to invite experimental subjects to campus right now. So it's a bit delayed, but we will have biometric measurements of human subjects in the lab. So therefore, we'll measure their heart rate. We'll have more objective or higher quality measures. And meanwhile, we also record their voice, and we record using videos. So we'll have the visual modality and the audio modality. So that will be upcoming. The big downside, if you're using lab subjects, then there are issues with anonymity. It's very difficult to anonymize videos. So the trade-off here, if you want higher reliability annotations, you may have to sacrifice the public nature of your data set. So in this project, the models that we use are from the family of deep neural networks, in particular convolutional neural networks. I'll introduce that briefly. have to keep a high pace because you can spend a lot of time on that. And I'm pretty sure among the audience we have people who are already familiar. But by experience, if I don't introduce the definitions properly, I will lose people. It always happens. So I like to say I created about 5 years ago, I created a course where I introduced machine learning to social science students. And what I like to say to social science graduate students is, you are an expert in machine learning. You just for some of you, you just don't know it yet. And I've tried here in one slide to show how similar, if you have a course in MLE or generalized linear models, you are already familiar with the core components of deep neural networks. So in machine learning, we'll call, instead of having the GLM inverse link function, we'll call that the activation function. But usually these functions are the same, like the softmax or logistic cumulative distribution. The objective function, if you've studied MLE as a grad student, you've learned that we're looking to express the log likelihood function, and we'll try to maximize the log likelihood to solve for the parameters. In machine learning, we're using the cross entropy, but that's just the negative of the log likelihood. So that's pretty much that's very similar to things you're already familiar with, even if you didn't have background in machine learning. And then the solving algorithm, that's the thing that finds the parameters for you. If you're using R and solving a GLM model, it's probably using the Newton-Raphson algorithm. You could use the gradient ascent. It's very similar for machine learning. You have sophisticated algorithms to solve the parameters. But in this case, since we're using a cross entropy, it will be within a variant of gradient descent. So the only thing that really changes compared to traditional social science statistical inference is that instead of focusing on the parameters themselves, we're not trying to have standard errors and parameters. We want to predict. We want the model to be very efficient at predicting the outcome variable of interest, for instance, sentiment, into new data that were not observed when fitting the model. So we'll use, contrary to when in social science, when we compute the R squared or the person correctly predicted using our own data set, in machine learning, as we will do in this, when I'll present the results, we're using a held out set, we're using cross-validation. You want to compute the accuracy, to calculate the accuracy of your predictive model based on data, on new data that was not there included in your data set when fitting the model, to reproduce how good this model will be at predicting the outcome variable in new data. So that's that's one of the key difference with the tradition in social science statistics. So I'm pretty sure all I've said in one slide. Tell me if you're able to do better than that in one slide to compare machine learning and classical social science inferential statistics. But if you understand that, then deep neural networks is really just an extension of that. If you have hidden layers, if you have a regular logistic regression, you only have one output node and several input nodes. That's essentially a special case of neural network. The difference is that we'll have hidden layers. So let me just use this. If we have deep neural networks, we'll have intermediate steps between the output and the input variables, hidden nodes or hidden layers. So these nodes here are hidden, which is essentially just nested functions, nested activation functions, or nested inverse link functions in the terminology of GLM. And if you have multiple hidden layers, we'll say this is a deep neural network. I often get strange questions, and people are confused, surprisingly, that what is a deep neural network? A deep neural network is just, it has more than one hidden layer and therefore is deep. So these are the models, the family of models that I'm going to discuss today. And in particular, one of the most, probably the most useful deep neural network that you will want to use if you study textual data and audio data are convolutional neural networks. So again, I'll be fast because I know some of you are familiar already, but just to make sure that the rest of the presentation makes sense, this is an illustration of a one-dimensional convolutional network, so 1D CNN or 1D ConvNet. So the convolution operation is very useful to model data that are sequential. So if you're studying textual data, you will have a sequence. So your one observation is not just a vector, as would be the case if you have survey data, but it's actually a matrix. So if you have a sentence as an input, this sentence is a sequence of T words. So is hypochondria a symptom of COVID-19 could be your sentence. Each word will have, I call that features, but each word could be encoded as a multinomial variable. So therefore it could be a dummy variable, zeros and ones, or a one hot encoded vector for each word, or it could be some other representation. So you'll have different features or different variables for each word. So we have a matrix that's just one observation, and convolutional neural networks are very useful to model data of that nature. So instead of having just one coefficient, we have a filter that we will take the dot product between this filter, this set of coefficients, to compute the hidden layer. So instead of having, as was the case previously, as shown here, only one set of coefficients, we're using a filter which could have a length. We can specify different lengths. So here I'm illustrating a filter of size 2. And the convolution operation is that we will slide that filter and multiply the input variables with the coefficients. So these are the coefficients we'll be solving for. And these are the resulting values in one hidden layer. So we can have multiple layers of convolutional network. If we continue sliding, we still take the dot product and put the result in the hidden layer. So as you can see, it's slightly different than what we may be used to in social science statistics, but it's not that different. We just have more coefficients, and we're using a special type of operation called convolution. Notice that you can have multiple filters. That's a very brief introduction to that. And obviously, if you're really not familiar with convnets, you'll want to read a little bit about it. But the idea is that you will typically have more than one filter of coefficients, and therefore your hidden layer will be a matrix itself. And these different filters, these different sets of coefficients, will capture different characteristics of your input data. So it could be a specific attribute, whether a text sounds negative or positive, or whether it expresses anxiety or calm, and so forth. That's what we hope for will happen through in our neural network. What are the current trends? So these are the building blocks of the models I'm presenting next, but the current trends right now. So if you in the audience are thinking about studying text and or audio data in your own research, well, the current trends right now for audio is to use the raw audio signal. So in other words, the wave file without any transformations as the input in convolutional neural networks. So that's a big trend. So no need to do any kind of pre-processing. Use the audio signal itself. Another trend that is rather new is to use transfer learning. I'll emphasize this concept a lot. I'll clarify what it means, but there are big models, pre-trained models that are trained on very large quantity of audio files that can be used to improve the accuracy of a model that you are interested in applying with a smaller data set. Same thing with text as data. If you want to do machine learning with text right now, it's all about transfer learning. So that's the key thing. Previously, when I started working with textual data like 6 years ago, word embeddings were the big thing. Right? And for years, people have used word embeddings as a transfer learning approach when fitting a predictive model using text data. But since the past few years, we've seen new models that are much more sophisticated than word embedding. So right now, the trend is really using these models. And I'll, in this talk, so the model that we'll use is the BERT model. So a little bit on that in just a second. I'll add a bit of information. So what is transfer learning? So by the way, the concept is very controversial. So because it's just loosely defined, but it's essentially, to summarize what I just said, as is our case with these political videos, we want to predict sentiment. We have training data, but it's only a few thousand videos. We don't have so many observations, but we can use pre-trained models that have been trained for a different task using a very, very large number of these either audio files or images or text, and use this information, this knowledge, to inform our local model. So that's a transfer learning in a nutshell. And I'm pretty sure some of you using textual data have read or heard about word embeddings. That's a typical example of, in fact, transfer learning. So the word embedding model originally is you're trying to predict the surrounding words that appear in a text. So for any given word appearing in a text, you're trying to predict the surrounding words, and you have the reverse version of that. You can try to predict the next word based on the surrounding words. But it's essentially a very simple neural network with only one, so it's not a deep neural network. There's only one hidden layer. But the thing is, you can train that model on a very large quantity of text, and you learn to represent words with numbers based on how good they are at predicting the surrounding words. Therefore, this model, for instance, could have learned that afraid and scared are similar in meaning, therefore have similar embeddings, or similar vectors of values linking them to the hidden layer, because they help predict the same surrounding words. So they can be used as substitutes. If you have only a model with 1,000 documents, like 1,000 political speeches, and you train your model, you couldn't expect your model to be able to learn that scared and afraid have similar meanings. But using a model that has already been trained on a very large quantity of data, you can have representations for each word that capture this knowledge. And therefore, what you can do is convert your words into these word embeddings, which will be a numerical representation of each word that adds some information about the nature of these words. Words that are similar to each other will have similar embeddings. And then you use these representations to fit your local model to predict, for instance, sentiment in a text. So that's transfer learning. That's one example of transfer learning, using feature representations from a model that's been trained on a much larger data set for a downstream task. So for BERT, so the new trend right now, this was one of the most popular model of 2019, the BERT model. It's very similar, it's sort of similar, the intuition is very similar to word embeddings, but we have now a deep neural network. And one of the tasks, this model is trained on a very large data set of text. You take each sentence, and one of the tasks to train the BERT model is that you randomly mask one of the words, and then you try to predict what was the word in the original sentence. So it's like a model that trains itself to fill in the blanks. That's one of the tasks that model is trained with. Just like word embeddings, you can have embeddings from that models for each word, but what you can do is also add a classifier, an output node on top of that model that is adapted to the task of interest, for instance, predicting sentiment. So that's what we do as our benchmark. That's the state of the art right now for text as data. So if we do that with our model, adding an output layer on top of the BERT model using the transcripts from our video clips, and we try to predict sentiment, activation, and anxiety, here's what we get. We're really good at predicting sentiment. This is not surprising. There's been a ton of literature on sentiment analysis, so using text as data before. So we reach, for instance, an accuracy that is close to 90%. It's always good to look at measures that take into account the fact that the split may not be 50-50 between positive and negative. So here the proportional reduction in errors tells us that we reduced the errors by 73% using the model. So that's pretty good. It could probably be increased to 90%. I'm showing you the results using high quality annotations. That's about half of the examples from the video collection that I mentioned before. So those videos for which we're sure that the annotations are of good quality. The thing to note here is that if using text, and even using a state-of-the-art model, if you try to predict activation or anxiety, the results are really not as good as for sentiment. So in other words, this parallels, by the way, a recent study by Cochrane et al. That looks at whether human coders who watch the videos or who just read the transcripts of the same speech, whether they are consistent with each other in terms of coding, activation, and sentiment. And their conclusion is that the sentiment is in the transcript, but the arousal is not. So if you have coders reading only the transcripts, they won't agree with each other in terms of whether the speaker was activated. This information isn't there in the text, which sort of makes sense. And so one of the justifications behind this project is to see if we can measure or quantify these attributes that are not there in the transcript itself. All right, so now audio as data. Now that I've introduced all the key concepts, we'll essentially use the equivalent of the transfer learning methods, state-of-the-art transfer learning methods that we use for text with audio. And I won't go in details. I think it would be repetitive if I were to go in details about the sound, how sound works and how it's digitized. But you can check out this past IMC presentation by Christopher Lucas, who did a fantastic job presenting these things in more details. But essentially, a wave file is just a vector of integers. It's a series of integers. They'll usually convert it to float if you read them using a software, but that doesn't change anything. These are just numbers that are sequential. So just like with textual data, we're dealing with sequences. And usually, so depending on the sampling rate, so the quality of the audio file, you will have, say, 16,000 of these numbers per second. So the sampling rate is expressed in hertz. That's the number of cycle per second. So 16,000 hertz means there are 16,000 data points per second. That's a lot of information, much more than we have in a textual file. And essentially, when we produce sound, we're looking for wave patterns, because when we produce sound, we're essentially making vibrations, and the signal that we have in our wave files will reproduce these vibrations. So therefore, we'll have like a sinusoidal shape that you'll retrieve a sinusoidal shape, waves when looking at the data and plotting them over time. As this is, by the way, here, this is a speech from Barack Obama from one of the videos in our data set. All right, so again, I won't go into the details that have been covered before, just for the sake to avoid redundancy. So briefly, what we're using here is the equivalent of the BERT model in a sense, that we are using a model that has been trained on a very large data set, 1,000 hours of speeches. That's the Libri speech data set, using a very large model. This is, by the way, this comes from Facebook research. And the model tries to predict the next sample, so the next bit of information in an audio signal using the one audio signal as input. So essentially, that's very similar to the BERT or the word emitting model. We're trying to predict the next words or the word that was removed randomly from the input sequence. So now we're trying to predict the rest, the next sample. So a sample in an audio signal means the next data point from the model. And once this model is trained on a very large quantity of data, it has learned to represent the audio, the original audio signal into feature representations, similar as word embeddings. For in this particular case, with this model, for each 10 millisecond, we have a feature representation, a vector of numerical numbers that sort of summarize this chunk, this segment of the input wave file. So we can use this representation to build a model. So here we're adding layers of convolutional networks and our own tasks. So our three labels or annotations are trying to predict. So we have an audio signal, we convert it to the features that comes from this pre-trained model that improves the representation of our audio signal based transferring knowledge from a larger data set. We add a classifier on top and we try to predict sentiment. So and anxiety and activation. So in this case, we have results that are better than text for activation and anxiety, and much worse than text for sentiment. So that would be one of the main conclusions that we observe no matter what we try, by the way. But these results are not really impressive. So one of the things we notice that one of the problems you will face is that if dealing with audio data is that speakers have very different voices. Every voice is unique, and women will speak different, have a voice that differ in general from men. An older person will have a different voice style than a younger person, and so on. So you can think of that the same thing if you're familiar with panel data analysis or hierarchical data. You want to account for these speaker specific or individual, you would like to have individual intercepts to account for that. At the same time, we want to be able to measure, to have, so if we were to use an individual or speaker specific intercept, that wouldn't help if we want to predict the sentiment or the anxiety of new speakers that we don't have at the training stage. So what to do? So in this, we keep using transfer learning. There are some fantastic models that have been created for speaker verification. So there are models that are trained specifically to model, to represent what is unique about each voice. And by the way, these are the models that can be used for deep fakes using the voice. So you can reproduce or clone the voice of someone using these representations. So by the way, these are the vector representations from this model. So same principle as before, we're using transfer learning. And these are representations of the voices of Barack Obama and Elizabeth Warren. So each voice type will have a representation that captures the essence of that voice. So just to show you, if we plot these voice encodings, or we call that the speaker embeddings, we notice that using principal components analysis, we notice that voices of women tend to be similar to each other, and voices from men tend to be similar from each other. We even notice that Canadian accents are different from American accents. So these speaker embeddings capture properties of each voice that are specific to our speakers. So what we do is that we fit our final model using the feature representations discussed before that sort of capture fundamental components about our audio wave signal, and then we concatenate that with the representation that are designed to capture what is unique about each voice, the speaker embeddings that I just mentioned, replicate the model, and now we get a very good results for activation, almost as good as text is for sentiment. we have an accuracy of nearly 90% using the high quality annotation videos. So you can compare here, if without this control for the type of voice, the results are almost 10 percentage points lower in some cases. So this seriously improves the accuracy of the model. And here I'm just showing you the impact of annotation quality. So if you include low quality labels, the impact is almost is worse even than not considering the fact that voice styles are different. It's even here we drop by almost more than 10 percentage points in terms of accuracy and proportional reduction in error. By the way, OROC means the area under the ROC curve. I should have mentioned that before. So in summary, audio as data is very good for activation and anxiety, better than text. So these attributes of speech are not really present in the transcripts, whereas text is much better for sentiment. So despite all the improvements to our audio model, text is transcripts appear better at capturing sentiment than audio. By the way, so this presentation is over now, but we have we also considering the visual modality. We'll have in this project. So we'll ultimately the goal is to compare the three: text, audio, and visual. I can tell you that visual modality is very promising. So again, the key points here: audio seems, according to our results, better at capturing aroused or activated and anxious states. Text seems better at capturing sentiment. So there's a bit of a complementarity here between the two modalities, text and audio. Accounting for speaker heterogeneity, so the different voices and types of voices in your sample matters. And also the quality of human coding. If you're working with sentiment, emotional states, is a big issue that will affect accuracy. So that's something we're revising right now. The feedback is welcome. I hope you enjoyed this presentation. I should conclude with two quick thoughts. If you like audio and video data, I think I should warn you, if you haven't started using audio and video data and you think about starting, so I should warn you that first, you'll probably get addicted to it. It's fascinating, it's fun, it's interesting. And the second warning is that it takes time. So just processing the videos, as I explained before, is complicated. So that's really not, don't wait until 2 weeks before MPSA or APSA before starting to write or to analyze the audio or visual data. You'll get into trouble. So you need to be willing to invest the time. Thank you so much for those who are still there among Justin's viewers, and yeah, feel free to ask any questions and feedback. If you want to collaborate to this project, feel free to reach out to me as well. Thank you.
Thank you, Ludovic, for that presentation. At this point, Ludovic Rheault is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And while we're waiting for some questions from the audience to come in, I'm going to ask a couple of questions that I had during the talk. So one thing I was thinking about while you were discussing the role that neural networks play in this process and what neural networks are, one way of understanding as I see it, and what I'm really asking you, this is not more than a comment, more of a comment than a question. It is a question. my question is, like, I conceptualize neural networks with hidden layers as essentially mapping observable variables into features and then the features into outcome space, right? So basically it's a little bit conceptually like transforming observable variables into principal components or something, and then trying to use those principal components to predict the outcome. And then if you have multiple hidden layers, you're creating features which then predict other features, which then predict the outcome. Is that essentially what's happening when you process audiovisual data with a neural network?
Yeah, I think that's a very good summary of the intuition behind neural networks. What I think is helpful to to understand what's happening is to think in terms of interactions. You'll see there's no interactions here, but social scientists, you're usually familiar with an interaction term that you multiply two variables by each other, but something similar is happening. So you have multiple hidden nodes in a layer, and some will be positively associated with two of your X variables or two of your input variables. Another one may be positively, the next hidden node may be positively associated with the first variable, but negatively with the second. So it's the same as having these conditional effects. So the more you add layers, the more complex the interactions you'll be able to capture. And as of course the trade-off, a model that will be too complex will probably have poor accuracy in any case. So you need to have the right level of complexity. But yeah, same thing that happens both with text and with audio. So the interactions between words, or the type of sequence of audio signal that you have will be modeled. The interaction between the observable components of your input signals will be modeled by deep neural networks in ways that are sort of complicated to understand. So I won't get into the discussion of whether, some people will say, oh, it happens in a black box where it's difficult to interpret. There are techniques that allow you to interpret what's happening more precisely. So sometimes you may just ignore what's happening and all you care about is accuracy of prediction. But that was a long answer, more of a digression on the topic that you just raised. But essentially, I think the description or the definition you gave gives a good idea of what's happening. Yes.
So I want to link the first half of the talk to the second half. I'll start by saying this. I know about a very sophisticated, highly developed neural network that is excellent at extracting sentiment, and not just sentiment, but also activation and specific emotions from audiovisual data. And in fact, we all have one, right? It's our brain that we do this all the time. And in the first part of the talk, you were talking about using human coders to extract some sort of ground truth. And I guess one thing, there are two kinds of questions I want to ask. The first question is, what are we getting out of this neural network that exists in the computer that we wouldn't get out of the neural network that exists in our brain, right? So in other words, why are we doing this? Is this just an efficiency issue, or is this really about getting content or understanding that you can't get from human coders?
Well, that's a very good, interesting question for a discussion. But yeah, so definitely the theory behind deep neural networks is to reproduce essentially how our brain works. And essentially what the model is trying to accomplish when being trained on data that have been annotated by humans is to reproduce how a human would process the information and arriving at the same conclusion. The ultimate goal would be to reproduce how the human brain works. The main reason of why using this model as opposed to human judgment is, so I'll come back to what I was saying at first. So the C-SPAN collection itself for the US alone is 250,000 hours. So you could ask your very competent undergraduate students, say, watch this for a year, all the videos, and there will only be a tiny fraction of that collection. Take note each time, knowing that you're very good doing that. So it would take 1 year, and then probably when that student comes back, you will say, oh, I don't like the scheme, the annotation scheme anymore, so let's do it again and change something. So this would be really inefficient, and we would like to be able, so we have this huge quantity of data, 40 years of recorded activities in Congress, and there are probably things that we've forgotten about, we've never studied because there's just too much data. So if we're able to train a deep neural network to reproduce what a human being does and being as good as a human being, we may have biases, and humans may be may fail also. So that's one issue we're facing. But let's say that we're able to train a model as good as a human. That would be fantastic. This model can work night and day in a fraction of the time, analyze all our videos, mark them, quantify variables that we never thought we could have before, sentiment activation, and so on. And this will allow us to answer many interesting substantive questions that could be about how do politicians react in terms of crisis? How does anxiety affect their behavior, the decision-making process? Does that make them more conservative or more risk averse, and so on? So yeah, there's a question of efficiency. Like these machine learning in general can essentially multiply or increase our ability to annotate and code and quantify data sets in ways that would never have been possible before.
So we have some questions from the audience, and I'm going to ask the first one, and then I'm going to actually expand on it a little bit. So Hanyu Sun is asking or says, both audio and text have pros and cons. Is there a way to combine the two approaches? And my expansion on that is, I'm reminded of the 1960 presidential debates between John F. Kennedy and Richard Nixon. And there's an anecdote that those who listened to the debate thought Nixon won, but those who watched thought JFK won. And I'm wondering sort of if that kind of synergy is present, maybe even for video data.
Yes, definitely. I think ultimately the goal, that's a very good question. And indeed, we heard the same anecdote in our Canadian courses on political behavior and political communication, the Nixon-Kennedy debate. So yeah, that's a very good point. In this talk, we started by comparing. We want to understand how each modality works individually, but very good point. The next logical step would be, and some people in engineering and computer science already do that. So they combine different modalities in a single model. So with the flexibility of neural networks, it will be possible to have two types of inputs in the same model and use audio and text, and therefore leverage the benefits of each modality. And in fact, we could have three different modalities at the same time. So ultimately, this will be the goal. We're just sort of going step by step here in this particular project. Like, we want to really carefully understand how each works individually, each modality works individually, and then combining them. Great point.
I have a question from Jose Benke of the University of Michigan ISR. He asks, can you comment on the limitations of your approach due to the quality of coding and annotation? You mentioned that data without unanimous, I think it's non-unanimous, agreement was excluded from the training set. This presents the methodological challenges as well as concerns about biases in your training sample. How can we improve this part of the methodology?
Yeah, so that's the step we're working on right now. So I've shown that it was very brief at the end, but that this really has an impact on accuracy. So the simple solution is that we need more annotations. Like here in this case, we have three different annotations, so three coders. So the question is, so we find that just 2 to 1, like the majority of 2 versus 1 really has a negative impact. And if you think about the previous the previous comment that Justin made about the human brain, this model can only be as good as a human is. It'll reproduce the same, it will try to achieve the same conclusion. So if your human coders do not agree, then your model can only be as good as humans who disagree, and will be confused as your coders are. So I don't have, I think the question that was raised is really good, and we're looking into it. I don't think I have the perfect answer. So right now is that the videos that we know are not consensual, we will have more coders coding them so that we'll be more confident of about the label. We'll also we're also adding videos anyway, so we're continuing this process, but I'm very open to suggestions. I think there's the question of whether it's the selection bias. Normally you don't want to select on the outcome variable. I'm really interested in that question theoretically, so you're probably read these books in political science that when you're doing research and you're trying to make inference, you don't want to select on the dependent variable. So you probably all heard that. But the thing is, here it's a predictive model, and whether the same logic applies, it's different. It's not something that I would have the time to say something clever about in the 3 minutes that are left for this IMC. But it's that's the center of our preoccupation. So we understand the question and the importance of it, and we're open to suggestions as well. So if you have a good solution, because we want to make this data set public. So in fact, it would really be helpful to have suggestions so that the data set meets the expectations of people who would want to use it to sort of find an even better models in the future. So yeah, it's very difficult. So adding coders so that you achieve a greater level of uncertainty. Adding more videos is always good anyway, so we're doing that as well.
Well, we have two questions and like about 2 or 3 minutes left, so I'm going to try to get through these as fast as I can. Jos Elking asks, perhaps a bit beyond the scope of the project, but do you have an idea of how much measures of arousal and anxiety are based on elements of the audio that are related to the spoken language, as opposed to other audio elements like tone? In other words, is this transferable to other spoken languages, or would you have to completely retrain the model? And I actually want to add to that, you know, even people who speak the same language don't always derive the same conclusion about a speaker's intentions or meaning. You know, just look at how we interpret what Donald Trump says, right? It's very partisan. So do you have to retrain the model for different languages? Do you have to retrain the model for different types of people or schemata, or what?
Actually, so that's a very good question, but that's part of the more general problem of speaker heterogeneity. So you can have different, so languages will sound different. We think the solution is to account for this variance. You want to, if you don't take that into account, that's sort of analogous to the problem when we first showing the model, not taking into account the fact that we have different speakers. By the way, we have 2 different languages in our dataset. We have some of these videos are in French, so we have 2 languages in Canada. That explains my weird accent as well. So I'm a French native speaker. So that's a very good question. You need, so what we're capturing here, my interpretation is that it's the tone, changes in the tone that are not, but if you do not account for these this variance between speakers, and you were to throw in Portuguese and English speakers together, not minding that, then it would be an issue. I should emphasize that the paradigm, the idea behind deep neural networks is that normally you shouldn't have to care about that, because using a very complex model, it will learn to distinguish speaker attributes from the tone and so on. However, this works if you have like hundreds of thousands of videos with so many observations that you can trade a gigantic model that will do that. In practice, if you have a small data sets of a few thousand videos, you still need to correct for that. That's sort of one of the main key points in this presentation. But yeah, that's a very good point.
Well, and the other question is actually really pretty much a kind of a follow-up. Sebastian Vallejo is asking how well transfer learning, both for audio and text, works for data in other languages. So for example, how well are these models trained in other languages, or how well do they translate? So you were talking about the neural network automatically adapting to multiple languages, but this seems like it would be more of a problem for the transfer learning learning methodology.
So I didn't have the time to go in details, but if you're interested in using the BERT model for language, for the text as data, I think it's now available in 70 different languages. So it has been trained for different languages. So especially for text, yeah, for text, you really need a model that will, one issue I haven't mentioned that is obvious, but if you have words that are out of the vocabulary during the training stage, you won't be able to represent them. For instance, using word embeddings, you have to have a vector of zeros. So you will need a model that is trained in the language. But these are, it's fascinating that the quantity of work that people are putting together, the scientific community is putting together, including the work from companies like Google. So the BERT model comes from Google researchers. So it's now available in 70 different languages. Similar for audio as well, you have models that have been trained in a specific language. So there are aspects of the voice that I think go beyond. So audio is different than text in that text you really need to account for language differences. There in the audio data, there's a bit part that is more universal in nature, but still. So usually in transfer learning, you have models available in different languages if you want to apply that to a specific language. And that's very good points from the audience.
Well, it's 1 o'clock Eastern time, so I'm going to go ahead and end the seminar. Thank you very much, Ludovic, for being our presenter this week. I think this is a great presentation, one of my favorites this semester. I want to remind everyone that this presentation will be posted to our website shortly after the broadcast in case you'd like to share it with a colleague or watch it again later. This is our last scheduled IMC presentation for academic year 2019-2020. We are in some preliminary discussions about possibly expanding the schedule given the COVID-19 outbreak, but we have a lot of hoops to jump through and things to coordinate before we get there. So watch your email. We might have an announcement to make, but for now, this is the last scheduled talk. If you want to rewatch any of the talks given this year, they're available for viewing on www.methods-collouqium.com. And if you're interested in giving a talk in the IMC in the next academic year, when hopefully most of us will be back to our regularly scheduled lives, please contact me at justin@justinessery.com or see the website methods-collouqium.com that I just mentioned. Ludovic, thanks very much for being here today.
Thank you so much, Justin. Thank you for having me.
And stay safe, everyone, and hope to see you next year, if not sooner.